So yes, my name is Jorge Castelo. I did my PhD in Santiago de Compostela in Spain. I mainly focus my studies in spinning boson stars, mainly. But then I have like some side projects, and one of them is this one, because it has to do with spinning boson stars in different regimes. So what we did during my last stages of my PhD and the short postdoc I did in Valencia, the first of this year, was to use some of these bosonic models to try to understand with them the dark matter that composes the halos in galaxies. So the title mentioned the two-component bosonic dark matter model, but as this paper was a follow-up of another paper using only one dark matter component, I am going to explain the basics of to use one component to fit the dark matter halos, and then again make the points and the changes when using the two-component models. So the first of all is to see the motivation and origins of this problem. And in the first years of the last century, people believe or think that the most accurate models for fitting galactic rotational curves were done just by taking the luminous matter, because other matter was not visible, and we weren't aware of this thing that we know today as dark matter. So the expected was the rotation curve to follow a Keplerian decay following this kind of law. But first Tricky, he was studying the clusters, galactic clusters, and he realized that the movements of the galactic clusters couldn't be produced just by luminous matter. Then people start to make observations, empirical observation of rotational curves, and they reach the conclusion that we were missing something in the movements. Why? Because if we study the observational rotational curves, that is how matter moves around galaxies, we expected, if we take into account what we see, luminous matter, we expect this kind of decay. If the matter reaches this area, then the rotational curve would decay. But instead, what we have is a flatten on the curves. And we have the luminous part described by luminous matter, but then the data, the observational data, do not decay, but still maintain flatter. So this was the rotational curve problem that was found, as I said, last century. And then with the problem, a lot of possible explanations emerged. And some people thought that could be the modifications over the Newtonian gravity for explaining this phenomenon. Others suggest that maybe we were lacking some matter, and then the dark matter theories allow. Other people just suggest that maybe there were compact objects, big compact objects that we were not seeing. Many theories. But then people study more and more data, and they realize that what we were missing was a halo, a kind of spherical halo composed of we don't know what, but we could not see that. And this was the amount of matter making the galaxies moving like that, and also the matter around the galaxies moving like that. And many theories emerged with that. And yeah, as this is the problem, I think that this is understandable. So what we have is that there is a lack of matter in the galaxies, and we don't really know what is there, but we need models that are not that do not emit light and can be fit the observational data. So there are like many families of models exploring that problem. So the point is that I was focused during many years studying the spinning bosonic models, bosonic stars and proca stars. And I saw some works that use that models under a certain regime to explore that ideas. The point is that people did these studies using static bosonic stars. So what we thought was maybe if we take a spinning bosonic star in a very specific regime that we will see is the Newtonian regime, but doing everything under the general relativity laws without approximations, and then going to that regime, maybe we could explore that these bosonic models explain in some sense the halos. We will see it. So the first thing that we tried was to explore the scalar bosonic, let's call start by now, but then we will see that is more like a scalar field diffused and occupying a region the size of, well, more than a galaxy. But the gravity is going to couple the scalar fields and bound them. And yeah, we have this metric that is axially symmetric, spinning, and we have to solve it, of course. We couple the metric with the following stress energy tensor, that is the canonical form for a complex scalar field. So what we have here is, as you see, nu, alpha, beta, and omega functions of r and theta, because everything is spinning. And then we have a complex scalar field, also depending in r and theta. So we have to solve the following system, that is the Einstein-Klein-Gordon, for the field to fulfill this axially symmetric system. The ansatz has to be in this way, that we have a profile. It's not really a profile, but a surface profile, and then the harmonic part. Here we have the field frequency, the harmonic index, and those are the parameters for the scalar field, and those are going to be very important because we will study our systems just focusing in the values of n equal 1, that is the fundamental spinning model. But then this value, omega, can vary, and this is going to be the thing that determines the compactness, the mass, the radius, and everything. So this is the parameter of the problem. Then we have the Einstein field equations and the Klein-Gordon equation. And by doing crazy numeric stuff, we can solve the problem and find this is the field distribution over the space of a spinning boson star, a common spinning boson star. And here these colors just determines the phase. Okay, but these objects are invisible, at least in the electromagnetic spectra. We can see them only by gravitational effects, because as you can see here, the stress energy tensor do not couple to electromagnetism. So we have an object that is invisible, but can reach masses very different, because I forgot to say something here. Here, this is the potential, and this potential depends on mu. Mu is the mass of the boson, and everything scales with the mass of the boson. That means we can change this mu and then obtain objects from different regimes, from sizes like neutron stars to sizes of galaxies. Also, this potential can be very different, can have, apart from the massive term, various self-interactions, and this will play an important role and make the configuration very different, more or less massive, more or less stable, more or less dilute. So this part, the part of studying bosonic stars, scalar boson stars, it was done by us. We just studied a lot of different potentials and obtain solutions for all the available field frequencies. So we had like a bunch of solutions, and we can work with that. Then we also, in my work, we also work a bit with proca stars that are also bosonic stars, in the sense that the thing that we are coupling to the gravity is a bosonic field, but right now it's not scalar. As we will see, is vectorial. Here, the metric is exactly the same with the same dependencies, but the stress energy tensor is very different. As you can see here, this is also known in particle physics sometimes as massive electromagnetism, because it follows the equations like the common vectorial field, but we have mass here. And rather than the Maxwell equations, what we have is the Einstein-Proca system, where we have Einstein field equations with the stress energy tensor and curvature. And then for the equations of movement, we have the Proca equation. Here you see, this is the answer for the field. We have the same kind of harmonic part describing the axially symmetric behavior as it should. But then rather than a unique surface or profile, we have a vector of functions depending on each coordinate. So this system numerically is going to be harder to solve, but still until that point, we had these solutions done, a lot of scalar solutions, also vectorial solutions. And what we want to study is if we are able to find rotational curves, at least orbits, for these objects that could be compatible or comparable with the part that a halo reproduces in a rotational curve. So, yes.
Previously, you said that boson stars are invisible in the sense that they have no an electromagnetic interaction.
Yes.
Here, for Proca fields, you do have an electromagnetic term. You say the same?
But this is not, this A mu is not the electric part. It's not a photon because it's massive. So it's not coupled. Despite the equations look like a photon, this thing is still invisible to light. It's a boson that is not. If we wanted to couple this to electromagnetism, we will need another vector and make the coupling with the derivatives. And we could see it if we treat the system under another kind of stress energy tensor. But those are not coupling with electromagnetism. So yeah, here what we have is we can study the orbits just by studying the geodesics. So we derive the equations for an orbit for this kind of axial symmetric metric. And then what we have is to compare whether our models show up a thing that is comparable with our models. And here is the interesting point. This plot shows the velocities that can acquire matter around a scalar bosonic star in the spinning regime. And as you see here in these labels, the velocities are really high. This is 10 to the 3 and 10 to the 5. If we study the Proca systems, the velocities range from a few kilometers per second to 500 kilometers per second. This is all in the Newtonian regime, okay? In the part of the model that we shall explore. And the point is that for observational rotation curves, we cannot reach over 300 kilometers. So, yeah.
Sorry, just a question, confused. So here you are showing the system with some velocities, but at one point you are not dissipative effect here, so you're not pulling to gas. So what are the initial conditions you need to observe?
The initial condition for obtaining these curves. Okay, each of these curves, here we are not taking into account anything about temperature. The point here is that for each model, we have a field frequency that tells us how the field internally behave. So for each internal field frequency, we will have a different star that will rotate with a certain velocity. And this is what is defining the difference in curves. As you can see here, we have this parameter that is what determines the model. It's just the field frequency and the rotation. So this is going to tell you how dispersed is the model, how compact it is, how the matter around it will move, but no thermal effects in here. So as I said, by studying different PROCA models, we see that we can reach the velocities coherent with the observational ones. This has a reason, of course, and it was not clear at the beginning, but if you remember the plot I showed you before for the scalar field case, the distribution of the matter is kind of toroidal. So toroidal distributions are really more inert, and the quadrupolar moments are going to be very high. So these inertia properties for the scalar stars against the PROCA ones that are more spherical makes the matter around them to move with higher velocities. Okay, this is the drag. It's a frame that is being dragged by the rotation of the object. You have gravity. You make an object gravitating with some spin, and matter around it is going to rotate. This is the geodesic movement.
I have a question. You are assuming only the gravity of the bosonic star. Do you consider also the disk gravity? Or?
We will see. Yeah, that's a very nice point. That was just for having the description of this object, this halo, only alone and making the movement. But now is the point that you were saying, description of the matter. And as all of us know, in galaxies, we not only have the halo, but the luminous part. So the scheme is like that. We have sometimes a bulge, then we have the disk that can be made of gas and stars, and then we have the halo. Our point here is that by choosing models for the luminous part, then we want to fit the observational curves by assuming our halo is the good one. So the first part now is just, this is going to be the velocity for the whole system. And here we have to describe the disk matter, the galaxy, the gas matter. This is due to stars and objects. This is due to gas. Then the bulge if necessary, and then we can add this part that is going to give us the dark matter halo. Then there is something that we are going to explore also, that are the so-called the subhalos. But now, just for now, let's focus on this part. And this is going to be given by the rotational curves observed by the geodesics of the PROCA. So the description of the luminous matter in our work was kind of, let's say, naive, because we just want a luminous description that was nice. We did not enter in very deep details, because I know that there are some other approximations for describing the stellar disk and the gas disk, but we just take some that we know that works. And for the stellar material, we just take the Freeman approximation for the disk. This looks difficult, but it is not. Those are some Bessel functions. And here in the sigma and this R and E, the observational information, because these models are obtained by taking observational data. So this part of the disk is quite well described by using this approach. Then for the gas, we just take the information of the surface distribution of the H1 lines in galaxies, and then obtain the mass distribution, and obtain the velocity is easy just by is the integral of the mass, and then is the typical Newtonian behavior. That is what we expect. And also for some galaxies, we have a possible bulge. So again, the bulge is a standard thing in galaxy physics. we took the Sersic parameterization for the bulge. Again, we have some functions that take into account these parameters that are observational parameters. So the point is that the luminous part in our models are described by using observational data. And then again, we have now two options, two paths. That is to work with these bosonic models I presented. And we have two parameters. For each model, we have the field frequency, that is what I said, and then the mass of the boson, okay? So the mass of the boson, at first, we don't know the value of the mass of the boson. We have to explore which masses allow to the right distances and total masses. And there is another option that is to use the main halo as in the previous case, but just fix one mass for the boson for all the galaxies. Because in this approach, we can use different mass of the bosons and field frequencies for sure. But this has a problem that is, in this approach, we are suggesting that different masses for the boson exist. Okay, could be, and we explore that point. But then we also explore another option that is and arise naturally, as we will see, that is fixing one mass for the boson, and then try to get the right full fitting by putting a second component for the halos. So I am starting by just explaining how to parameterize this kind of subhalos, and then we will see the results. So there is a way of having, is also studied in literature, that we maybe have two components halo, one that is the main one, the principal one, the big one, and then some dark structures around. Sometimes they put these subhalo theories in the machos. You know, the machos are massive astrophysical compact halo objects. But we studied these subhalos in a regime that is not having trouble with the machos limitations. We will see it. So the point of studying subhalos is that we can, in a region of our galaxy determined by some internal and external radius, we can have a distribution of these objects that we don't really know the masses or sizes. The fitting is going to tell us, and then we will see if it has any sense or not.
Just one question. Do simulations, technical simulations with bosonic matter or scalar field, they already produce subhalos and halos? Can you use that for the statistics of sizes and masses?
Could be. We did not, because we just take the observational rotational curves and compare with our models.
For the abundance and
okay.
Yes.
I didn't check that, but it would be very nice, because one of the main problems is to then, when we have our predictions, check with other simulations. So we can study that. This is a nice point. So we need a distribution that puts these subhalos in our galaxy, and I am lacking of time, so I am going to be fast here. We just use some cumulative distribution functions to obtain the exact, well, not exact because this depends on any parameters, but for having a radial distribution for the subhalos, and then having the positions in our model for these subhalos, we need to use a Gaussian kernel for making the point position not to be a point, but to be a kind of distribution. Okay, so as you can see, well, I am going to be quite fast because I want to show you the results, but we can obtain, by using this cumulative distribution function for having where these subhalos are going to be, and by using the mass distribution for each subhalo, we can define a mass function for this total amount of subhalos, and then we have another dark component. for the overall system. And what we studied here was the previous function to treat it like these subhalos are going to be, why not, scalar boson stars. We can just, it could be also Proca boson stars with another different value for the mass, but we just assume to take different subhalos composed of scalar boson stars that can be spinning or static. And with this, we just make some bounds for the scalar mass, the mass of the boson. Here we have some numbers, but
I'm sorry. What is the fraction of mass in subhalos that you consider?
The fraction of mass. You mean the mass of each subhalo?
Well, if you add up all the subhalo
Okay, you will see.
How compares to the whole?
We will see, because it depends a lot. But I don't know if I have in the presentation, but for sure that we obtained that. It was like less than a third of the total halo mass.
Typical in CDM is, I don't know, 3%.
3%.
There are
very few.
Very few.
Yeah, we will see it, because it depends a lot.
Okay,
Okay, we will see. Yeah. So then what we did was to fit various galaxies. These are observational rotational curves. And we try first without any subhalo, just by putting the main Proca halo. And we saw that our results, just by using one, well, this was the first paper. We were exploring these ideas, and we find nice results. And as you see for our models, having the luminous part and the halo described by a big Proca halo, you see the results are quite good, because take into account, we have to understand here that we are only using two parameters for the halo, and one of them is going to be nearly fixed. So depending on the field frequency, you see here that the frequency is in the regime of Newtonian things. If this value is close to 1, that means that the massive halo is rotating not very fast. Okay, that is what we expect. And the mass for the boson is in the order of magnitudes that it should for the Proca case. If we were using scalar bosons, this value would be very different. But for the Proca case, it is okay, and it has not conflict with observational things. So as you can see here, for these galaxies, we have more or less nice fittings. You can see here that in this part, we have an overfit and then a lower fit for these two galaxies. We have more of them. You see, those are bigger galaxies, and the fittings are quite nice. Just by using this Proca halo, we are not solving the problem, let's say, but we are having very confident models in terms of the observational rotation curves. And we checked like 10 or 12 galaxies, and for all of them, depending of course on the characteristics of the galaxies, and we have to take into account that the luminous part was done by using very naive models, not the most realistic and accurate ones. But the point is that if we check again the masses of the boson and the field frequency, we will see that we have a very small range for the boson mass and the field frequencies. And then we conclude this part by saying that the mass of the boson should be something between 6 and 34 times 10 to the minus 26 eV, and the field frequency has to be between these values. And with that, we can just fit a lot of different galaxies in a very good way. But then there is a problem, that is, we don't want different masses for the boson. Well, ideally, what we expect is to have one mass for the boson. Despite those are very close, but let's say we want one mass, and then we can add something just to see if the remaining part can be determined by something. So what we did in the first study was just fit the galaxies the other way around, try to fit better the first part, the part shared with the luminous matter, and then try to find a function that we were not certain about the source of this extra function, and then try to find something that matches with the lacking part. So this comes the second work that is just, well, you see, is from September this year. And what we did here was just, let's fix the mass for the boson, and let's add some subhalos. And here, what we found is that the number of subhalos times the mass, the total mass, is going to be the parameter that allows us to fit the total curve. So depending on the galaxy, the number of parameters and the mass is going to vary, of course. We now add errors to the study and study which model is the best by using a chi-square fitting for each galaxy. And what we find is that things improve a bit in some models and really a lot in others. For example, here we can compare the fittings with only one halo and with subhalos. You can see here that things are getting closer and closer for some models, and those are the worst we see for some galaxies than, for example, look, if we look at these parts, you see that the part that subhalos give to the total is small. We studied the masses in the paper. I don't remember, but it was like a tiny part of the total is due to the subhalos, because the mass of the big halo was trying to just fit everything. What we did was only take a lower fitting for the total halo and then add a small part of subhalos. And as you can see here, the results are quite nice. Of course, for some galaxies are worse, but in my opinion, this is due to the luminous part that is not very rigorous with reality, because we don't know about these fancy simulations in galactic physics. We just take some models that work nice to explore the role of this dark matter here. And that's all. We see that by taking a small amount of subhalos, we can obtain really nice fittings by taking that a kind of Proca field around the galaxy is playing the main role of the main halo. And everything was done, as I said, in the non-relativistic limit, but with relativistic simulations, we obtain everything in terms of general relativity, but we take solutions close to the non-relativistic limit. Then we have, in this way, a model that can fix one mass for the vectorial boson, and also some possibilities of have predictions of the masses of the subhalos and also the masses of the boson particles that would produce these subhalos. And then, yeah, I think that we still have work to do, because we use a small set of galaxies, different galaxies, for not lying in the topic of only taking the ones that are good. But we study like 12 galaxies, and we now can study more. Also employ better models for the luminous part. That would be an improvement. And we can even try with different bosonic kind of fields, because we study only spinning scalar fields, and spinning vector fields in terms of only a Proca field, but there are more vectorial fields that remains Proca and are something else. And yeah, it would be nice also to implement a supermassive black hole for the galaxies that we know it has it in the origin, and then study this problem with a supermassive black hole inside, and then couple the bosonic potential to the black hole, because if we study it separately, it's giving interesting things, but then it would be better to take into account the gravitational potential that one thinks due to the other. So, of course, the halo is having a gravitational imprint in the luminous matter, and the other way around. So, if we want to study properly, then the thing would be to study the system all coupled and then try to see the effects of the gravitational potential. But well, still a lot of things to do, and we also can play some Halo games. That is also nice. And that's all.
Thank you. Questions?
Okay, let's go in this order.
Okay.
Okay, please.
Yeah, so thank you. I wanted to ask, how do you fit the various components, the disk, bulge, to each of your galaxies? Which observables do you use to?
Okay, I have it here because I don't remember. We take the information in various papers. I have it here in the paper. I think that I have a table. Yes. Here, the luminosity, the radial part for each disk, and then we use this ratio between total mass and luminosities, and also for the gas, the H1 lines. Those are observational parameters that we took from different works, more or less recent. And then with these parameters, we fulfill the models and obtain and we checked that this luminous part was well done with other papers that do it in the same way. So in this point, of course, it is not the most realistic thing, but well, it ran. So.
Thank you, Jorge, for your talk. Let me see if I understand the model. Are you trying to explain the effect of the boson stars and vector and Proca stars from the galaxy separately, or you are trying to put together the scalar field and the vector field to explain the halo superstructure in the
Okay, that's a point that is interesting. In the first try, we just take a vectorial Proca star and we use it as a main halo. Just one huge kind of vectorial field coupled to gravity for describing the halo. In the second attempt, we use again a massive, huge vectorial star for the main halo, and then we just add some substructures that are not, in the sense, they are not coupled one to the other. It's like we put one, and then we put the other substructures there in this region and study the overall effect that they have. It's like I think that this picture is what can explain this the best. Here, you see this dark gray is supposed to represent this huge vectorial Proca halo, and then we just add some substructures that are in this case we studied in terms of scalar bosonic stars, but those could be, I don't know, other Proca stars with different masses for the vector boson, or even unknown things. But we studied in terms of bosonic stars because we have a control over the total masses in terms of the mass of the boson.
But it's not, I think that one different way to put two fields is in only one model. From the
You can do that.
Lagrangian, you can add the Broca field plus the scalar field.
Sure. This can be done. It's Scalar models and can be done. But and that way was not explored, and maybe by doing so we can just without any subhalos to fit. This was that I mentioned that we can do that, or also a real scalar field making the role of the interaction with making the role of the mass of the vector field that is called the Broca-Higgs model. These kind of models can be also studied, and it would be very nice because maybe without any subhalo you could just obtain the right fitting. So you are right, you can do that.
One question. Okay.
Okay, I have many questions also. Okay, first, can you show some of your fits?
Yes.
The ones where it's very heavy, this component. Like that one?
This one.
No, those one, for example. If I understood well, you calculate geodesics in an equatorial. Okay. You should be probably careful because at least in the Newtonian case, those two models are unstable. Actually, the whole purpose of assuming a dark matter halo is because when people put a spinning disk and its own gravity dominates, it's unstable. Could get fragmentation, could get a bar or something like that. So those two solutions for the group one, if I understand, yes, it's the stellar disk.
You mean the luminous matter?
Yeah.
Okay.
It is unstable. So
okay.
Your observation wouldn't be this rotation.
Okay.
So I don't know if a relativistic effect
could stabilize. Okay.
But that would be maybe a good avenue to study.
Yeah, that's a nice point.
The other thing is, can I do the other one? Okay, for the subhalos.
Yeah.
At least in the axion-like dark matter particle, when you have this range of masses, like minus 22, 23, the Broglie wavelength is at the scale of hundreds of parsecs. So you have quantum fluctuations that behave a little bit like subhalos. And on top of that, you are adding subhalos. So my question for you would be, because you're doing geodesics, maybe you can do in the future lensing.
Lensing, yeah.
Because
it would be nice.
Constrained to the amount of substructure. Maybe this is the right model, but
or maybe not. It just
should be
but
careful.
yeah, sure.
You have a lot of fluctuations. People already see anomalies in the flux in strong gravitational lensings, but they don't know if they are compact star clusters, another thing, or maybe the subhalos. But maybe you should be careful that you don't put too much substructure.
Sure.
Could be a lot, but okay.
This point was also when we send the paper to the referee. He or she tell us you have to take into account this point. We try to make some justifications just by looking at the scales where we obtain the masses to the subhalos to be. But you are right that sometimes we have to be cautious because there are some restrictions, observational restrictions through lensing that has to be into account. Yeah, you are completely right.
Thank you. More than that, it's interesting that you're mixing two models. Maybe I should do that.
Who knows? Yeah.
Any other question? Very naive question.
Yeah.
Maybe stupid because I have no idea what boson is.
Okay.
Let alone boson matters. Where did they come from?
This is not a naive question. This is this is the question. No, we don't know. It's just a model,
Okay, if you don't know, is there any way to detect them somewhere else?
Yes, bosons can, well, the main line of detecting kind of bosonic matter right now is just studying gravitational waves, because of course we are treating here some bosons that are very, very low masses and then reproduce things that are huge. But when you treat the bosonic matter in other regimes, what you have is like an object that is kind of neutron star-like or a black hole-like, and just by watching collisions of these things that we don't really know what they are in gravitational wave science, sometimes you can fit better this phenomenon through bosonic objects, size of a boson star, of a neutron star or a black hole, or in the mass gap. And this is right now the easiest way, just by using gravitational waves. But of course, by lensing could be also, because these objects are compact enough to deflect light. So you could observe something that we think is a black hole, maybe it is a boson star. And there are, of course, what we have is different models. And then we check with observations also for neutron stars and black holes. We check, and the model that better reproduce the observations is what is expected to be there. So in this sense, by gravitational waves and maybe light deflection would be the paths to detect these things right now. Well, there are more things, but
Okay, final thing. You mentioned the drugs, so they are in gravitational interaction with the baryonic matter.
yeah.
Are they supposed to be also accrete on the matter, change the characteristics?
Could be. For sure that it could be. But we didn't take into account yet, because it's quite hard to put everything in a unique gravitational system and study the accretion around and how one potential affects to the other. There is a group in Prague that is studying it.
In
But
addition to this, we have turbulence viscosity, which we also don't understand
Yeah.
very well. But at least we can see the effects, the change of temperature, the other physical parameters that we can measure.
yeah, sure. And right now, this is like the first steps. So we don't not study the more physical effects that due to these halos will have. But it's like in the work to do list to study also at temperature if possible, or how to even movements of clusters and how putting these would affect other things. But you are right. Of course, this is a naive model in the sense that we have to evolve a bit for having better things.
Can I
Yeah, sure.
comment on the question? So basically, you can accrete this bosonic matter, and because you don't have turbulence or emission, you can see the change on the black hole or the compact object mass. This is how you can measure.
This
the
is not
accretion.
in the black hole. This is in the.
Yeah.
Yes, I'm talking in the black. Yes.
Yeah, here we are in a regime that is far to the center. So yeah.
Yes, very interesting discussion. So I can see in your future work, you are just considering to go to small scales. But why are you not considering to go to the galaxy cluster?
Oh, it could, that's a yeah. That's a point that we suggest at a moment to study it, because we are studying here the role of the matter in the galactic zone, but we know that there is also dark matter playing a role between clusters, and also how the clusters moves depending on the matters they have. So for sure that's a work to do, and very interesting one.
Because larger the scale and less you have this very difficult dynamics.
Smaller,
For
yeah.
example, you can just delete a lot of viscosity effect when you are going to the very
Bigger skulls, yes.
And here you are already a kind of profile you can test and kind of stuff and compare with X-ray.
Yeah. That would be really nice. But as I mentioned, this work is from September, and I I'm just on it, but it's an idea, and I mean, this group in Prague, in the Czech Republic, they are working with this kind of stuff, and they are trying to making the things a bit better in sense of putting the gravitational potentials together and then couple the matter one to each other, comparing these physical effects. So yeah, you are right. A nice work would be studied it in the regime of clusters and higher scales. Yeah.